Okay, I think we can start. So welcome to the third webinar of the EDYCE project. We are near the end of the project, as everyone knows, but that does not mean that the contents are already all described. And now the measure of the things is ongoing. You will see on the website of the project the new deliverable arriving in the next months. And we are collecting now results for our demo cases, for the demonstrator of the methodology developed inside the project and the application. The third webinar is about demo buildings, lesson learned. Clearly, in the presentation that we will see today, we will not cover all the aspects that we discover in our demonstrator cases. So it's clearly important for the one interested to go after to the deliverable, to enter inside the site of the project, and stay tuned on this point. But it is interesting today to see how the application of the EDYCE approach and methodology may open a lot of potential outcome inside demo analysis, inside building advancement on the energy point of view, and so on. The webinar of today is looking at this aspect with a short outcome for all of the main demonstrators that we have inside the project. So we will have a presentation for the demonstrator in Denmark. We will have a short presentation for the Italian demo buildings that are in Tolle Pellice near Turin. We have a presentation for Swiss and Cyprus demo cases that we have. We have some outcome from the Living Lab that you have near Rome, provided by Enea. And we have also some thinking and outcome from the scaling up approach of the EDYCE, so for the territorial demo cases that we have in Switzerland. Before starting analyzing the demo cases, Professor Pomianowski for the Aalborg University will introduce us the EDYCE project, main aims, and also key development that has been done inside the project as project coordinator. I'll leave the floor to him.
Thank you, Giacomo. Thank you, everyone. Pleasure to be here. This is our final webinar, where we will focus on the results from the national demonstration activities in EDYCE, and my colleagues will, in a very short time, present you with, I think, very valuable insights in our activities that focused on operational assessment of the buildings towards the dynamic certification, as well dynamic simulations, approach to the model simplifications, etc., etc. Before that, I will give you in a very short version an introduction about the EDYCE and what it is, what the consortium partners are, and the general objectives, and then I will finish with the demonstration. Oh, I think something showed on the screen. Yeah. Just a moment, we have a small technical issue. Yes. So we will start. I will start with project identity, some facts about EDYCE, consortium members, motivation for the project, which was very important for us, why we do the job that we do. Then we'll move to the key objectives. Again, we will only focus today on some of the job that we managed to develop over the last 3 years. Then I will switch to the concept, and we will finish with the EDYCE demonstration. So the project EDYCE is the Innovation Action Project that is a Horizon 2020 project with a duration of 3 years. We started 3 years ago, we finish by the end of August, and budget is approximately 3 million euros, and we have 5 European countries, Denmark, Italy, Switzerland, Greece and Germany as a partners of the project. Moreover, we are 10 stakeholders, and among the stakeholders we have expertise from two universities, 5 companies, we have 2 municipalities and 1 national agency, which means we have a good a combination of the expertise, and we have not only the theoretical approach that is very often reflected by the universities, but we have also the practical angle to the tasks that we have been dealing with from the companies involved in the project. Who are we? We are Olbo, we are Polito from Turin, we are Estia, Core, Torre Pellice, MTech, Neogrid, GEP, and also the canton of Geneva. The motivation for the project was started by identification of the problem that is challenging, I think, all of the European countries, not only European countries, but of course we are more focused on these countries, which is the performance gap, which has been quantified by numbers from the monitoring devices in a large number of buildings. These monitoring devices can show us that the current asset rating methods are not very well suited to reflect the real situation in the buildings. Maybe some years ago they were suitable and more accurate, but with the changes and more demands for the building stock, these methods do not follow up. And what we can see is that they are very, let's say, overestimating the energy performance of the building, which means they are not, in reality, the buildings, the new buildings, renovated buildings, etc., the low energy buildings, NZEBs, are using more energy than anticipated and calculated by these asset rating tools. While, on the other hand, the old buildings, which are high energy using buildings, usually use less energy than rated. As a result, we have a mismatch, and we have a situation where reality is not reflected by the EPCs and the databases created of these EPCs. Another challenge is that related to the renovation of the buildings, where our theoretical anticipation for the energy renovation of the building are very favorable and reflect that we should expect a very high energy saving, while in reality the actual energy savings are much lower. First of all, because of the methods used for the calculations are not so realistic, and there is a well-known rebound effect, and generally there is a combination of different issues in the building related to the user behavior, system performance, boundary condition, loads, etc., that all together influence the energy use of the building in that way that new buildings or renovated buildings consume in reality higher energy than we theoretically calculate. The objectives of the project are methodology for dynamic certification of building based on openly available resources and tools should be developed. And here we did base this on dynamic modeling, and another leg of this activity is monitoring. So this is the use of the operational data from the buildings. The second objective is to develop integration framework. In our project, we have covered that by proposing a middleware solution, which is called Fusix, that was covered in a second webinar of this project that you can also find online. And then we also focus here on storing and linking the monitoring and simulated results towards the performance gap detection. The third objective is to increase the user awareness, both the tenants and experts, by providing them with appropriate key performance indicators. And here we have addressed this by Dynamic Energy Performance Certificate that collects key performance indicators that were identified throughout the project. Another objective is to facilitate the shift from the standard to adapted condition of use that I have mentioned to you. So very important activity for us to see how our assessments would be affected if we go away from the standard assumption that we use for the asset rating. We call this in our project adapted condition for modeling. This helps us to understand the performance gap, detect the potentials for the savings, promote free running operation of the building. The last objective is to test our concept in a number of demonstration buildings. And this is something that we will cover today in this webinar. Yes. Regarding the key challenges of the E-DYCE project, these are performance gap, which is the difference between the theoretically anticipated energy and actually used energy in the building that is monitored. The second challenge that we covered and addressed is the operational assessment, which is about bridging and collecting the monitoring results for comfort and energy, both in the building, and also by using the smart heat meter data for determining the space heating and domestic hot water separately. The third challenge was to investigate towards model simplification, because when we move from static calculation that are used nowadays in asset rating, when we move towards the dynamic modeling, this is more time consuming, this is more challenging, and we have to provide or investigate towards the modeling that is feasible. So it means something that could be actually performed by the practitioners. Another challenge was the communication of the results. So these are the KPIs and DEPC. Here we have identified 4 areas of the results, which is the energy signature, thermal and atmospheric comfort, and free running operation of the building. And then each of these areas has several KPIs that were identified. The last challenge that we covered was about energy prediction. And here we did a kind of interesting progress towards seeing if we have a historical data of the building, so from the operational data, how can we predict the next days, week, or months of the operation of the building. This is especially interesting if you would like to monitor building drifting away from its historical operation. Now, the last slide is illustrating to you the demonstration cases that we have in our project. We have demonstrations from north to the south of Europe. The most north demonstrations are in Denmark. Then we have several demonstration cases located, I would say, South Central Europe, Switzerland, and Italy. And then we have south placed demonstration in Cyprus, in Nicosia. And on top of that, we have also a scaling up activity that Florenzo will tell us about when we go from a couple of buildings towards a building stock of Geneva Canton. So very interesting study. On top of that, not only we have a geographical coverage of the boundary condition, let's say that the buildings are exposed to and different ways that we build the building, so the building characteristic, but I think we also have international expertise reflected here. How do we approach the different problems that we have in different countries, because we have different problems, how we are exposed to when we work with modeling and operation of the buildings. I think this is also very interesting that you will see that in the next presentations. If you would like to reach for more, we have our social media, LinkedIn and Twitter, and we have our webpage, E-DYCE. There you can find more materials, and more deliverables will also come, the last ones, in the near future. So we are very welcome to see and visit us there. That is all. Thank you very much. And I will pass my voice to Olina, who will tell you about the Danish case.
You should hear it. Hello. That's it. There we are. That's what I mean. Thank you and good morning. So my name is Elena, and I have a pleasure to tell you a little bit about the Danish demo cases. And we will start with a very short introduction. What is it that we consider among our demonstration buildings? For the Denmark, we have three not family houses, these are apartment blocks. These are 3 to 5 stories apartment blocks. All of them, they belong to the different housing associations. These are the buildings from the social housing groups. And if we look from the left to the right, we are having the buildings in Hornbæk. We have buildings in Tulevej, and finally here we have to the right Magisterparken. All of those 3 buildings, it tips. No. I'm not allowed to move now. So all of those buildings, they have been through some refurbishment over the years, but in this project we are looking into their operational performance, but we also look at the simulation results that could feed up with some information about the buildings. So if you are looking at the first building, this is the building that has the highest instrumentation level, where we monitor not only the total energy used for the whole building, but we also measure the energy used for space heating and the domestic hot water at the apartment level separately. There are also high level of instrumentation within the apartment, the measurements of the room temperature in all of the rooms, the measurement of the air quality through CO2 concentration in many of the rooms. Furthermore, there are sensors on the radiators, so we know the flow of the water for the whole apartment for heating, and we have the window sensors, so we know when the openable windows are open. It does not mean that we monitor all of the apartments, but we monitor only the selected apartments within the building. Then we look at the building number 2. This is the building that has the least monitoring equipment installed. This is mainly related to the window sensors and the room temperature. And finally, the third building, which is Magisterparken, this is the building that has an intermediate level of monitoring. I guess sure. Yes. Maybe much easier for everyone. Thank you. So if you're going then looking at those buildings, the only main difference among those is the type of the ventilation system used. So we have the mechanical ventilation in Hornbæk, natural ventilation in the 2 other buildings located there. And one of the main, or one of the challenges that we were looking into, that is the, let's say, disaggregation of the data. And as Michael have already mentioned to you, what we often look at, we would like to be able to compare the energy or performance of the building, which is monitored, to the simulated data. And if we are looking more specifically at the space heating and the domestic hot water use, very often we have a big challenge in monitoring the domestic hot water use in the buildings, because most of the smart meters that we know within the buildings, those measure the total energy, so combined heat and domestic hot water. So by having the idea here that by having a minimum amount of information at hand, we should be developing a method that can allow us to split those values, so we can have monitored data for the space heating and for domestic hot water separated, so we can compare those with results of our simulations. And some of the work has been done within this area. We are not going to talk much about it. The references that describe the methodology are provided. And the initial work here was to actually find a methodology and show that it is possible to take the data from the smart heat meters and divide it into the space heating and the domestic hot water use. The initial methodology developed within this project was good, but it required a high quality of data. It means we are not allowed to use the average hourly values, but we actually need to have the data at a higher precision level, which is typically not available for our buildings. So the continuation of the work was using the information from the meters for the cold water to feed the methodology and thereby improve the prediction possibilities. And this method has been finalized and it is published now, so you are very welcome to read in the papers. Besides the focus on the domestic hot water use, some of the things that have been looked into, as already mentioned by Michael, about introducing new performance indicators, among those the energy signature, but also similar types of indicators. Over here on the figure, you can see the 4 apartments, 4 figures. Each figure shows 1 apartment. These are on the y-axis, we have the flow for the space heating, and on the x-axis we have the temperature difference between the inside and outside. And what we can see, these are the 3 apartments that look very much alike. These are the apartments that actually have very different behavior, have very different room temperatures, but the last one, this is the one that behaves differently. And this is mainly because this is the apartment, we can see from the measurements, is heated by only 1 radiator, 1 water-based heater, and thereby the heat released into the space is not used efficiently. So this is an example how the monitoring information can feed more, or monitoring data can feed us with the information about the performance of the different living spaces. And this is the figure that is showing that we have 3 with the similar apartment, and then we have 1 apartment that has a very bad heating efficiency. And of course, this information we can only have if we have the split of data into the space heating and the domestic hot water. If those monitorings are combined, then we would not be able to see that. Then moving on a little bit more into the direction of the simulations, we have focused a lot of work on the defining and reducing the performance gap. And one of the concepts here is that the performance gap to some degree is caused by the dynamics of the building, by the variations that happen within the living spaces or during the day or during a week. And of course, by introducing these dynamic building simulation tools, we are able to address those in our models. But one big question is, what does it take from us as engineers or modelers to model this behavior? Can we really reflect this behavior through our models? And this was one of the objectives in this study. We would like to look at the simple models for simulating the dynamic performance of the building and a little bit more complex models. Furthermore, we could also have a possibility to test the application of our adapted conditions in order to test the hypothesis that we introduced in the beginning of the project, that introduction of the adapted conditions should be gaining or should be supporting us in reduction of the performance gap. And over here on the figure, you can see one of the methodology. I will explain it in very general words, but you can have a look at it in our deliverables. The idea is that we can have a different approach to modeling the heating system. It can either be with a, let me see if I can make it work here. Yes, or here. So we can have an electric convector we can have an electric radiator, or we can model a more in advanced way, detailing the water-based heating in our model, and in this way we sometimes can hope to produce better results. We can do a similar approach at modeling the geometry of the model. We can design our models as a one-zone based model. That would be the one you see over here. That would be a one-zone model. We can make it a little bit more detailed. We can make a two-zone model depending on the orientation of our building. We can make zones on the apartment level, so every thermal zone would represent an apartment. That would be Z3 here, and so on and so forth, until we get to the point where we model every room of the building as a separate thermal zone. What we have done here, we have tested all of these potential possibilities, combining these into a large number of simulations, and then we could actually obtain the results. And our results, of course, from a very detailed model, that would be Z5 here. I'm not pressing that. So this is Z5 model that can produce as result with the resolution down to a room level, while the other more simple model can only produce the results at a building or a staircase level. In our study, we worked only with the staircase, so we are not modeling a whole building, but modeling one staircase. And depending on how you apply the boundary conditions, you can compare the results among the models and hopefully say something about what model performs best. And we have tried with two sets of the boundary conditions. So we did the first study where we say we use the comparative study. So all models have used the uniform, or let's say in agreement with the EPC definition, a uniform amount of loads, uniform set point temperature for the heating, etc. And then we compare the results. And when we look at the results here, speaking broadly, what we find is that for the modeling of the heating demand within the building, we find that actually the geometry of the zoning is not very important. And one of the reasons why it's not very important is because we simply look at all zones having the same set point temperature, and thereby there is not a significant variation in between the results for those zones. However, if we are looking at our results at smaller periods, if we are interested to know when the heating starts and turns off in the spring or the fall season, then actually the zoning becomes more important, because the solar radiation and the solar gains are the ones that would define in which zone the heating should start. If we are looking more at the thermal comfort, then we can see that the zoning does become important. It is very important to zone our model so that we can reflect those temperature variation, especially in the warmer seasons when we do the modeling. And some of the last results I have here is on the slide. When we on the first set of the graphs, the ones you can see over here. Yes, these are the ones. That is where we are looking at different models, already applying the variation of the temperature. So we actually impose different set points in the different rooms, and the definition of, not the different rooms, but in the different apartments, and the definition of those set points are coming from our monitoring. And we can compare different models. When you can see on the x-axis, as you can see here, these are the models named, and on y-axis we see the yearly heating energy demand. And in the orange bars, these are the errors produced for every model when we compare the monitoring data with the operational, monitoring data which is operational results with the model simulations. And what we get here is that many models, they perform in a more or less similar way. What matters, the model that has the highest results are the model that uses the space heating as a water-based radiator designed as a whole heating system in the model. But what is interesting, if we are moving from the top figure down to the bottom figure, this is a figure where we impose the people load in our models according to how the buildings perform. After communicating with the occupants, asking how many people are living in that apartment, once we impose number of people in the model properly, we are able to reduce the error in our simulations to such a degree that actually the decision whether we detail the heating system or not becomes irrelevant, because we can reduce the error quite significantly. And similarly, if you look at the right-hand side here, we are looking at the results presented at apartment level. And here we are seeing several apartments. What we do here, we can see several sets of bars. We can see here 4 bars, then 4 bars here, and so on and so forth. The first 4 bars is one apartment modeled by several models. And again, the 4 next ones is the same. And we can see that when we have the standard people load, actually the degree of error in our models at apartment level can be quite high. And if we are continuing and trying to impose a real number of people, we can reduce the error to some degree. But we have a quite significant reduction of the model error is when we are applying the set points at the room level in our model. And then you can tell me then why is the last bar here is very, very high. And I will tell you that this is caused by the fact that our measurements are not detailed enough to express the room set point temperature for that apartment. And I'll show you an example in a moment. So here you can see those 4 apartments again. One apartment has more or less uniform temperature in all rooms. This is what the colors are for. They represent different rooms. The next apartment is very similar. Then we have the apartment down to the right. This is the apartment where they have quite different set point temperatures in the rooms. And finally, we have an apartment where we monitor the temperature only in one room. And this is the case for that apartment, that apparently the temperature that we measure in that room is not representative of the average temperature in the apartment, and thereby the performance gap for the model in this case is increased. And the figure to the right, you can see here, that is the average apartment temperature over the year if we average for each apartment separately. And then we could say, fine, we know that we can reduce performance gap to some degree, but when does this performance gap takes place? And one of the things that we see through all of the models, that a large share of the performance gap appearing belongs to the spring and fall season. This is the time when we have difficulties to predict the heating demand. And the example here we can see are the results of the monitoring and results of the simulation, where the orange line is the monitoring and the blue line are the simulations. And this is again results for all 4 apartments, and the apartment left down to the left, this is the apartment where we're not reflecting the set point temperature properly. And then, of course, one significant issue that we have is additional heating use over the summer. This is very critical or characteristic for Denmark, you could say. A lot of occupants are running the heating even in the summertime, in particular for the bathroom floor. And now the final slide from my side, some summary of what we have found. What we are coming to conclude is that actually the use of domestic hot water can be estimated by support from the model if we have the smart data meters operating properly. The complex geometry models, when we are trying to simulate the heating demand, at least for the Danish cases, those can be omitted if we are only interested in the heating demand. On the general terms, on the longer periods, as a month, for example, or a year. However, if we are looking into more shorter periods, as a weekly data, want to know about the activation of the heating system, then a little bit more advanced models would be advised. That is also valid when we know very little about the adapted conditions within the building. If we do know more about our building operation and we have a possibility to define the heating set point, then it can benefit, or we can benefit from going to more detailed models. And of course, one good learning from here is that the definition of the heating set point based on the measurement of temperature in one room might be a more drawback than the benefit to use in our simulations. Finally, for the indoor air quality, we have not talked much about it, but here we can see that the detailed models can be needed, but also much more information can be required in order for us to determine and account for those non-uniform occupancy patterns. That's all from me. Thank you. And I think that now Giacomo is presenting the cases for Italy.
Thank you, Elena. Okay. Okay. So regarding the Italian demo cases, we only remind that we have 5 buildings. We already have shortly introduced it in the first webinar, so you can also recheck it online on the EDYCE web pages. We have 2 school buildings. One is a public, and 3 residential demo cases. They are all located in Torre Pellice, which is a medium to small municipality near Turin. It's interesting to know that's very representative of building styles in not big city in the Italian territory. If you look at the distribution in Italian municipality, the dimension of Torre Pellice is also very representative, like potential expansion of the outcome in these demo cases. One of the things that we pursue, and it's similar to what was done in the other demo, but clearly each national background will support minor changes in the approach, is based on deep inspection in demo cases, to prepare and to produce monitoring plan, the installation of sensor able to cloud connecting support real-time measurement inside this building, energy, electricity consumptions, but also temperature, CO2, relative humidity, and other thermal comfort or visual comfort, other aspect inside the building. And further that, having the sensor connected, we also develop models of this building to support energy and comfort simulation of the building itself. Thanks to the monitoring data, we also have calibrated and tested the validity of these models above the monitored databases, using in the cases of Italy, the E-DYCE platform, which we will see in a second, as a platform we have developed inside the project to support and automatize energy plus modification and management in a automatic and also, we can say, REST happy based way. After that, data are clearly elaborated to calculate KPIs connected to the DEPC, so Dynamic Energy Performance Certification, which is the methodology, the methodology developed inside the EDYCE project, and after also to apply what we had done to extended functionality that are also present inside the project. Since DEPC is one of the base on other work and dissemination in the project, I will focus today on the Italian point of view of some of the extended functionalities to the EDYCE approach that we applied in the demo. It's only to remind, clearly we don't only monitor building behavior, but also the weather around buildings, because to simulate them and to have an idea of it is also very important to have the possibility to resimulate and to analyze the data in the same condition, okay? Otherwise we may have performance gap due to that. The whole process in the 5 Italian demo is automatized here real time, we can say, or semi-real time, so we are able through the FUSI platform developed by Hemter to retrieve both simulated and monitored data, so detect the performance gap in between the two, and eventually evaluate with maybe the causes for it and have a post-intervention. The approach of the simulation and management of these KPIs in the Italian demo, and also in other demo, but especially there, support the test and verification of the E-DYCE platform, so Python real-time and dynamic and climate evaluation, that has been developed by the Polytechnical groups. We don't enter so in detail on it because it was part of other dissemination and publication, but clearly is what is a platform that allows to manage model input and model output using Energy Plus as simulation runner. Now, using it in a sort of automatic and semi-automatic way. So it can be run through the EDYCE physics middleware platform without requiring more manual intervention on the model to have real-time weather, to have tests on specific KPIs, and eventually to detect the performance gap. Clearly, it also have other potential functionalities that, for example, the sensitivity analysis, or performs through a very simple input managing. I don't know what will arrive if we will test retrofitting analysis, things like that we will see in some example. In addition to that, it clearly compute KPIs and can compute the same KPIs on both model output, so energy plus simulation, and also monitored data. That's very useful because by this way we can really compare thermal comfort calculated according to the same standard. If we look inside the extended functionality that we are testing, they are clearly a lot. No, I do not have the time today to enter in all. We will have a fast recap of some of these outputs, some of these aspects that we will treat, and after clearly I hope that interested audience will go and look in our fantastic deliverable that will be accessible on the site. That's clearly what we test. First of all, we clearly analyze the data. So we have extended indoor environmental quality analysis and check. We have something similar also to what Albo represented before. So analyzing if the system is working well, if you have some part of the room or the building that does not reach or has different comfort conditions in respect to the others or in respect to the expected. We identify potential problem on CO2 inside school to suggest how to improve them, and so on. And we also have added some extra functionality, like for example, in now one of our schools, we had the possibility, thanks to this project, to install and test 3 detached mechanical ventilation units. You know, after COVID and during the COVID, was the idea what came before, because the project started before, but under the COVID, this became an urgency. So it was very interesting to test different control strategies, compare natural, manual opening window with informed people, without informed people, and the mechanical control in the school. And after that, we have other things, free running analysis to support and analyze how a thermal discomfort in a building does not have a system, may become a false, fictitious energy, and may have an idea to label it eventually. That's something we will not treat today because it will require too many times. We will also develop the possibility to test and analyze renovation analysis, so suggesting the professional how would be, on a cost-based approach, the impact of different choices in retrofitting the building, in terms of impact of specific choices and all choices together in respect, I don't know, to energy, to comfort, and to other aspects in the building itself. And this will be very useful because help the professional to go to a series of scenarios that after you will re-elaborate clearly like designer or like architects. And after that, we also have the possibility to test post-intervention evaluation, because in 2 of the residential demo houses, the tenants and the owners, during the project year, install more insulation, discuss with us changes of part of the heating system, and so on. So we have the possibility also to analyze on the monitor point of view, in this case, before and after the intervention, if it works, it will not work, and giving some general suggestion. And after that, we also have extended performance gap analysis, clearly, in addition to the protocol itself that is more standard like it is. While in this case, we can go demo by demo with some specific sub-analysis discussing with the tenants. And also this, we will really reduce it today in terms of analysis for the time. And at the end, the simplification analysis, in which we try to have an idea on how we can fast calibrate to the EDYCE platform the model, and how we can simplify the model, because to having a real-time simulation or something like that, we cannot have a model that require 2 hours for be run and after waiting for the time. So it's also important to have approaches that maintain the quality of the modeling in terms also, I don't know, subzone or zone, microzone outcome, but in the same time that is fast or can be run fast under request. So splitting the model in parts and so on. And last but not least, we analyze sensor distribution in terms of variations in between what it is monitored with under the same variable in the entire building, since we are in a research project, research and development project, so we have the possibility to put a sensor in each room, but it's clearly maybe too expensive, to think to disseminate, to expand the element in itself, especially in residential, so it was interesting to have an idea of variation arriving between room to suggest eventually a reduction in the number of sensors, and if you want to make similar analysis in larger buildings. Now I will go quite fast inside some of the results to give an idea of what we can get, okay, with the application of this type of monitoring, simulation, and platform itself, like the one that we are developing inside the EDYCE project. It's clearly evident that's an example of an extended environmental quality analysis performed in one of our residential buildings, a single family house, okay? So that's not a so large number of rooms, but it's immediately evident. Here we have thermal comfort in winter, predictive mean vote, so the fungal model. Here we have thermal comfort in summer, adaptive thermal comfort model, because it's free running in summer, heated in winter, no? And it's immediately evident the possibility to see that we have 3 spaces that stay in comfort, 2 are less used, and so the tenants correctly manage it, not to have a slightly cold comfort conditions, but reduce energy needs. But it's immediately evident also that we have a room with a very high variation that is not the one that arrives by the radiator system. And we will see why. And after that, we also see that in summer, in the free running, where a fantastic control, we can say in some way, even slightly cold, even if outdoor conditions are very hot, because it's a massive building, and clearly the tenants in itself has already done a correct management of the rooms. Now we see that it's more compact. It's also see that this part is more south facing in respect to the others, and in fact may have some more peak in the other condition point of view. The interesting part in this case in winter is clearly correlated to the fact that this room has a stove, we are in a mountainside, which is very used, and in fact causes a lot of variation that may reach even quite hot condition for a totally heated space, no, in a mountainside. And this is due, and we have clearly had the specific sensor to analyze it, that we have here the possibility to see that radiation activator mainly arrive and support morning, when the tenant does not have time to turn on the stove before going to work, while during the evening and the summer is the stone that mainly dominate the heating on this space. In some point of view, it's also possible to see that speaking with the tenants, we have some variation in the, you can say, management of the system, and after they have a sort of reduction in the energy consumption during the project year, okay, 10–15%, something like that. But that's interesting to know that this type of sensory may allow also to suggest, to analyze, to verify if radiators are correctly used in respect, for example, to the stove, if they need a thermal valve to avoid the fact that with the stove also the radiation is pumping in the same room, and so on. That's clearly support the fact that this type of analysis may suggest and support current management of the heating system, or eventually the cooling system. That's not the case, but will be, and especially to understand thermal comfort behavior in summer and winter, and eventually suggest to the tenants where to activate. If one room is a critical room for winter, potentially if you have more, it will reorganize, like in this case in living room and kitchen together in one for seasonal approaches and so on. If we continue in this type of extending analysis point of view, one of the others that we have done, it's quite interesting, is the analysis of what arrives to CO2 control in the school itself. We say that's open nation in Italian school, especially because we do not have the space and we do not have the mechanical ventilation in general. So testing, and this type of test is not so diffuse in reality, and that's interesting to see, because was also part of work in the ministry, not after the COVID, if needed or not. At the beginning, looks yes, after the cost, the complexity potentially suggests the network ventilation is sufficient if controlled. And that's quite true for what we get in this analysis. Now we install 3 mechanical ventilation units, remotely controllable, and we test 7 or 8 control solutions like Streich base, something more connected to double threshold or single threshold, and variation of the threshold in itself. And we look that with that we can control also the more critical rooms, like for example the smaller rooms with a lot of child. So when also opening the window, in some cases we may have problems in terms of CO2. But it's also interesting to see that the post-COVID evaluation, so when we have a master of the school that requires a specific, you can say, control logic in the manual operation, so each 2 hours you need to open and so on, the CO2 may be controlled. But clearly in this case, a monitoring is important to avoid, on the one side, to over-ventilate in winter, like arrives immediately after the COVID when the request is leave the window open. And you see immediately that the heating system increased the consumption and the temperature in the room, the average temperature fell down in some way because the dimension of the radiator is in a line, no? We can say. But also the opposite side to avoid the fact that you forget to open the window in itself. We also do a sort of small, we can say, citizen science analysis with students, and we need to ask them to control the window according to the sensor monitoring. So when you overpass a certain threshold, the sensor sends to you an alert. And that was very positive, we look, because the students, they were clearly, only can say, educated to do that. They maintained for 1 month, some 3 weeks, 1 month, this working, and it was evident that also at the end of these 3 weeks, 4 weeks of testing, they will still maintain an activation of the room. No, it's not only immediately after when we start the process that arrives. And that give a 10–15% improvement in respect to before. That's good. And in one classroom, we also get the same value, turning off the mechanical ventilation than was before with the mechanical. So that's very interesting. Clearly, what suggests this? That clearly sensor control ventilation rate is very welcome, both on the manual point of view to avoid overventilation, but also on the mechanical ventilation point of view, because when we see in the case in which we leave a sort of fixed air exchange lower to avoid noise problem or this type of things, no? We also have cases in which in this classroom we detect peaked, yes. To go very fast, the tool itself and the analysis also support the possibility to do parametric or sensitivity-based approach on the retrofit point of view. So it's not only a sensor of generating 5, 3, 4, or 6 scenarios, okay, of variation in the heating, the cooler system, the ventilation, the shading, and so on, but there is the possibility to variate this system with ranges, so different thickness of insulation, different thickness of position of windows, and so on, and to connect to them for what it is possible, also cost analysis, using regional or national databases of costs, so build your own. That's allow in some way to have the possibility to test the impact that the single action have in percentage on a large or customizable set of indicators. Final energy, primary energy, thermal comfort, number of hours above a certain threshold, CO2 eventually, if you are able to simulate like more in public building when you have a schedule of people. And that is useful to support in a fast way, we can say, a potential orientation toward the choice of correct scenario and reorienting of it. It's interesting to see that this type of tools of monitoring is very welcome also to give back to people, especially if there is small houses like, or also large public authorities, feedback, a fast feedback on the fact we have done something, it's evident. So some of our demo cases had the installation and was evident not only that they consume less because they see in the bill, even if the cost rise, but if you say, okay, stop, look at the kilowatt hour, it's evident this fact. But it's also evident the fact that slightly the comfort improve, the variation, the peak variation are reduced. When you add insulation, you may have some problem in summer of overheating, but you can manage inside the school, inside this building with fast ventilation. To conclude, when we look, and that clearly requires sensors. Sensors are generally quite expensive, especially if you want to have a reliable, accessible, reconnectable solution. But it's also true that if you look, for example, this graph, that the variation, statistical variation of monitored temperature in one of the school, each room, and also corridor and so on, in the summer season, and that's are the variation in the winter season. It's immediately evident that we have a general, we can say, behavior floor by floor. So in some way, especially for temperature, we can slightly thinking to reduce also because there is one thermostat. So roughly speaking, the south-oriented room will similarly act if there are people in. We have cases in which you see a variation, but that's another type of rooms with different schedule profiles of using. And also it's justified by that. So it suggests main rooms may have a general temperature sensor. If you don't control the temperature room by room, but if you want to control corridor, these type of things, minor aspect may be added. If you look at the CO2, in the building are not, in the residential is not like that, okay? In residential, we identify night and day schedule, and that clearly require at least 2 sensors, one for the 2 part of the building. Otherwise, we cannot really detect the behavior that arrives there. But on the school point of view, since the usage is in some way scheduled, we can detect that classroom have a sort of average approach till that they follow the same master required, okay, control logic. It's also evident the mechanical ventilation may have a slight differences. So to summarize, potentially temperature sensor may be reduced if you do not have specific control logic room by room, but you need one at least in the general rooms, the most used, and you need potentially one in the critical room if you use it in the season, okay? And it's also evident that on the CO2 point of view, it's true that you need at least one in the critical room and one in the standard room, because the behavior is similar if you apply the same schedule. But it's also true that, for example, for room, if you want to label or if you want to control, in Italy it's not compulsory right now, okay? But if eventually, if you need to apply some specific these EQ protocols, that will require CO2 diffusion. That's very expensive, but if it will be required, the market will push it. For this type of analysis, potentially you can forget and focus on a limited approach. Thank you. I will leave the floor to Tristan de Kerkhoff from Estia, so Switzerland and Cyprus cases.
Hi, thank you, Giacomo. Hi, I'm Tristan from Estia, and I'll talk to you a lot about Swiss case studies, and then a little bit about the Cyprus one that we also followed. So to introduce the 4 case studies that we have in Geneva, I show here the 4 pictures of it. So they have different typologies. 2 of them on the left are old buildings, so from the 60s and the 80s. And the 2 on the right are either renovated for the top right or newly built. When I say new, it's 2010, but it's like a high energy standards. So it's 4 different types of performance gap. And to monitor this, we wanted to monitor different buildings. So mainly the energy, thermal energy for heating and domestic hot water, but sometimes also electricity. And to allow to monitor comfort, we wanted to follow the indoor air quality, so the temperature, the relative humidity, the CO2, and sometimes even the VOC. What it looks like when we summarize a little bit the type of monitoring that we used is this. We had a lot of different monitoring types. And as you can see on the communication line, communication was sometimes difficult to us. We would mainly get CSV files, which is not ideal for, how would you say, a fluid data flow. So we will mainly focus here on this presentation on Centurion, which is the big building here underlined in green. And I'll talk a little bit about the Loire building because it's very interesting regarding comfort. So in Centurion, what happened is that we had a very large building. It's like 180 meters long. So we had to focus the monitoring on one alley. And we installed 22 sensors. So you can see them here on the right of the picture. So the red squares are the CO2 sensors, and all the other squares are measuring temperature, humidity, and the blue ones are also measuring VOC, although we realized later that this is something that we used definitely less in the E-DYCE analysis. And there are 2 heat counters, but for this time the whole building, so not only the alley, one for the total heat production, and then another one that counts the domestic hot water, the heat for the domestic hot water storage. So when we looked at the difference between the simulated and the operational data, we obtained this energy signature that is pretty dense. But what I wanted to outline here is that the operative measurements that you see in blue are in allowance, let's say, with the adapted condition that we were trying to calibrate with the actual building. However, after we obtained these results, we lacked the person that was handling the Energy Plus resources, and the further analysis that we did were mainly on the operational aspect, because we performed a ventilation change in the building on the 4th of April 2022, and this is the thing I will tell you most about. So what happened there is that we changed the ventilation system from a single extraction with no control of the inlets to something that depends on relative humidity in the room. Here on the right, you can see the airflow rates of the inlets and the outlets depending on the relative humidity inside the rooms. You can see that it adapts the airflow rate to, in sort of, the use of the space. So this was expected to improve both indoor air quality and the energy consumption, because it would reduce the total airflow rate of the building. So when we look at the effect of this change on the indoor air quality, and we look at the first graph, which is the relative humidity during the different weeks of the year of 2022 in blue and 2023 in green, we see an improvement. You see that the box plots mainly stay within the class 1 boundaries for the green boxes, as it actually reaches most of the time the class 2 limits in the blue one. This was much expected, as the ventilation flow rate was depending on relative humidity. So this was obviously the most easiest indoor air quality KPI to improve. Also, if we look at the CO2, and here I have box plot per hour of the day to see the effect during the night and also during the day when it's occupied, you see that the modular ventilation allows to ventilate when it's occupied, hence when the CO2 is produced, and therefore the CO2 measurements are strongly reduced. This was expected, and we're quite happy with this result. However, when we looked at energy, we weren't that happy. Let's say that we were expecting an energy saving that would appear quite strongly to us. However, first issue was that we installed a heat counter, as I said earlier, but this heat counter was only installed after the ventilation change. So what we had to compare before and after data with were the energy bills that are on the monthly value. So we tried to use the energy signature that you can see here on the right to see if there was an improvement before and after, but this is done on a monthly basis. And you can see that with the linear regression of the heating, there's no such thing as improvement. Here, yeah, we don't see the difference. So we could conclude that having only the monthly energy bill, if the improvement should be low, the energy signature was not the perfect way to see it. So we looked at the annual consumption. Here at the bottom right, you have what was expected from the simulation, so the ECO21 report, and what was measured. So we would expect heat consumption of 395 megajoules per square meter per year. And what we actually measured was 408. So the savings were a little bit lower than expected. When we looked at the different bills and we take it 12 by 12, we see that there's a reduction of the heat consumption. But looking into it, I mean, the change is here on the red line. But when we actually digged deeper and deeper, we realized, and this was like only 2 days ago, that in November 2022, the guy from the heating system decided to increase the maximal temperature. So it must have somehow eaten a little bit the expected savings. So this is something that they're going to change, and we'll see if actually it changes anything. So if we look at what we actually expected from the building, and what were the energy savings expected. If we look at the standard value, we would have expected something like 60 megajoules per square meter. Then if we use the static simulations, but with adapted condition, we would have expected 27 megajoules per square meter, so it's already reducing by 2. And if we go to dynamic calculation, then it goes even down to 19 megajoules per square meter. And what we measure is actually this 16. This really emphasizes the need for dynamic simulation to know how much you should expect as a saving, because this modular ventilation system is a dynamic system itself. So having static simulation, and even worse with standard value, really gives you high hopes in comparison to the reality. Now I'll just focus on comfort and the case of Loire, the building on the right on the first slide. This is a very old building and with a very old ventilation system of single extraction. And you can see here that the CO2 concentration on the top right for some of the rooms is super high. I mean, it reaches the threshold of 3000 ppm, which is not considered healthy at all. We realized that there was a night stop in the ventilation system. So by the time we discussed with the owner and everything, we had it changed by the 1st of November 2022. And you can see already on the carpet plot here that on the right side, I mean, it improved, not as its best, but I mean, at least it's not reaching 3000 every night in the winter anymore. The ventilation was set to continuous, and you can see the effects on all the CO2 measurements of the building here on the box plot at the bottom right. So you see that before the box plots are showing really high CO2 concentration values in all the rooms. And now 50% of the measurements don't reach 1,500 ppm. So this definitely improved the indoor air quality. It's not at its best, definitely not, but it was improved by this. However, when you look at energy, here we can see that it actually has a high impact, and it's a negative impact. We have single flux ventilation, so we lose more heat during the night, and this is easy to see on this graph. In the blue, you have the measurements before, and in orange, you have the measurements after the ventilation change. And this is weekly aggregated consumptions. And therefore, having a better comfort for the tenants actually here has a negative impact on the energy efficiency of the building. This night stop was definitely installed in order to have a better energy consumption of the building, but it was not good for the tenants themselves. And as there was no monitoring, I mean, no one could knew that. So to conclude a little bit on the case studies, on the Swiss case studies, I would say that the indoor air quality comfort, it should not be left out of the energy considerations. We saw in Loire that it can be unhealthy for the tenants themselves. And we saw also on Centurion that there are some systems that allow you both to increase the indoor air quality and to reduce the energy consumption, this modular ventilation that we talked about. And also, when you consider this type of technology, you have to consider to perform a dynamic simulation of your building. Otherwise, you would have high expectancies in the energy saving aspect. And this is what was outlined in E-DYCE itself. Dynamic simulations are needed for dynamic technologies. And in the Cyprus case studies that I'm sorry I don't have the time to talk about, but we have a lot of these dynamic technologies, and they all need this kind of dynamic simulation. So we have night and day ventilative cooling, thermal mass of the building itself, the maximization of the free running hours, the fact that you have ceiling fans instead of ventilation running throughout all of the day. Also, there are there's quite a lot of wind in Cyprus, so the cross ventilation and the smart control of the building itself. So I invite you to go read the final deliverable that we will soon submit to have a better eye on the Cyprus results, and I'll have to conclude the presentation here. Thanks a lot. Oh, this is French. I'll leave the floor now to Michele for Enea.
Okay, thank you. Good morning, everyone here in the room and online. This is a presentation by myself, Michele Zinzi, of a report that was done in cooperation with colleagues in Enea and at the Polytechnic of Turin. We are going here to present some outcomes of the exercise we did in our Living Lab, which is a bit different in comparison with the other case studies. This is not real case study. We worked a bit on the reverse way. In our Living Lab, we can monitor almost everything in the testing room, and we will see it. And from the monitoring data, we implemented a very detailed calculation model. And then, once we had this model calibrated, we could see how different input mode can affect the final thermal and energy performance of building. So the Living Lab consists of 7 rooms in a building in Enea Research Center Casaccia in the northern outskirts of Rome. In this room, we have individual air conditioning unit for cooling and heating, and environmental monitoring of air temperature, relative humidity, CO2 concentration, illuminance, and also presence. In 4 of these 7 rooms, we have advanced glazing system in which the solar shading and also the opening of the window for ventilative cooling can be operated both manually or through the energy management system we have installed in the building. These management systems allow us to monitor all the data of the different part of the Living Lab, as well as to implement different logic for the energy system and the dynamic elements. In this table, as an example, we reported the logic control for solar shading activation and window opening according to time schedule of physical parameters that are measured inside the building or in the external weather station we have mounted on the building itself. The monitoring part consists of 4 periods, 2 in thermal free floating in summer and intermediate season, and 2 periods with active energy system, 1 in summer and 1 in winter. And then we have also additional monitoring period that were dedicated to the specific task relevant for our study and for the project. As an example, to observe the difference between the operative temperature and the air temperature in our rooms, or studying more in detail the distribution of air in case of natural ventilation at night. Once we had all the data set of measured data, we started with a calculation exercise. The building was modeled with Energy Plus and also with the E-DYCE, the platform developed within the project. And the calibration of the model took place through 3 different steps. We started with measured data in 2020 in summer, where the project was not yet started, but then we verified the calibration in 21 and in 22. And to assess the reliability of our calibration, we used the procedure define relevant ASHRAE guidelines, which set the minimum requirements in terms of accuracy of the calibration. You can see here the calibration signature, which is very accurate, but also we check the accuracy against the ASHRAE procedure. We define for a building thermal free floating and for hourly data a coefficient variation of the root mean square error not higher than 30%. And you can see here in the last line that we were on the safe side of this accuracy by almost a factor 10. Once the model was fully calibrated in thermal free floating and in with active energy system, we started with our calculation exercise. Just to remind, I didn't say below that we have excellent results in terms of thermal free floating, while with active system we scored the performance gap in the heating and cooling mode of around 10%, but we will come later to this, which is anywhere in compliance with the guideline of ASHRAE. So to do the calculation extended at a seasonal level, we downscale the model complexity. That means same windows for all the same room, same set points, and same strategies. And then we define the building variance. There are an enormous number of variables to check. We concentrated on the most usual in terms of impact on the performance of building. The weather data, the internal gains, the summer night ventilation, which was relevant for our building, the winter infiltration and ventilation rate, and the impact of shading system. For each of these categories, we define some variants according to an Italian standard, according to European standard, or also according to usual recommendation, a practice for the building sector management. These are the results very quickly of the building in thermal free floating. This is the number of discomfort hour in the reference building, first column on the left. And here we are the results for the different variant. According to the relevant standard, this building should be in class C2. That means 2 degrees of difference from thermal neutrality for the measured operative temperature. The red would be class 1, which is for a weaker class of people, like elderly or sick people, which is 2 degrees. The one before was 3 degrees. And then we added the third class, which is C0, which means 1 degree of difference with respect to the thermal neutrality. We did this exercise because if you see the reference case, practically we are almost in the comfort condition. So we wanted to stress the results to highlight the differences. And we found out that there are in some cases strong difference when we change the input mode. As an example, the third group of bar is the results obtained with the standard Italian weather data. We have an enormous increase of the discomfort hour. And the same applied when we use as an example the standard occupancy according to Italian standard. We did this, or if you want to have another results, we can see the enormous impact of the shading device when we use fixed solar correction factor, while in our model we modeled the effective use of the shading device. We obtained also similar results when we moved from the thermal free floating to the active cooling use in heating, which are the red bullets, and cooling the blue bullet. Again, here we reported the relative variation in percentage. This is the base case, the reference, and then the variation according to the different measure. We have very scattered results. That depends on the modality, on the mode of input. If you look at, as an example, the class 2, which is the internal gains and occupancy, if we go to the standard, we have very high discrepancies, above 50% both in heating and in cooling. But when we do a relative simple adjustment, which are the indication by the relevant standard, the difference goes to 20% or below. In general, the discrepancies, however, were quite high for several cases, let's say 30, 40, or even more. And this finds an explanation when we go to the final analysis of our exercise, because we register in our study very low final energy consumption. That means If we scale down them to the whole heating and cooling season, final energy used by 4 to 5 kilowatt-hour per square meter. This means that also absolute variation, very low, like 1 kilowatt per square meter, implies a relative variation of 20%. So the results are affected by the absolute value of our energy use. Besides this, we found out the performance gap, which is almost always referred to the quality of the simulation, depends also on what happened inside the building, like the real set points against the fixed one, the position of the sensor inside the room, and some other issues that are typical of the building, of the room where we are working in. We also found out, related to the E-DYCE platform, that the sensitivity analysis during the calibration period was very heavy. It took a lot of time with a lot of simulation and analysis. But we found out that this part could be really scaled down in terms of analysis when we have some good data coming from the building itself, from the reality. And this could save a relevant part of the calculation work. And another aspect that we found out is related to the air conditioning system. That we have standards at international level which are quite accurate to predict the performance of the system. It could be at seasonal level or instantaneous level for COP or EER. But what happened in practice is that we cannot apply this standard because there are no data provided by the manufacturer, so we have to rely on very, very simple data. And in our case, it was not a big issue because of the low energy use we monitored, but for a high consuming building, this can be a real issue, especially now, living in a period where heat pumps will be more and more used also for providing space heating. If you want to have more detail about the study, this was a very quick extract. We will have soon online the deliverable D4 about these activities, and also you can find online the presentation and the paper of this activity we have done at an international conference in Japan in May. Thanks for your attention.
So you have seen all the individual case studies that cover a large span of meteorological and typological variation. I will show you how we upscaled the E-DYCE results with two stakeholders. One which was partner of the project, which is the Office of Energy, which is the legislative, no, not the legislative, but the Service of Energy that applies the energy law. They are editing the regulations to apply the energy law. And during the project, they had this task to perform. They should edit the new regulations. So what we are developing and finding in the project, it was directly implemented in the energy regulations, and this has finished in September 2022, and it seems to be very good, and the other cantons are inspired now from these regulations that completely changed from the initial intentions after several findings of the project. And the other stakeholder is the owner of the buildings. The 4 buildings that Tristan showed you is owned by a big company owning something like 550 entrances of buildings. Is something like 350 big buildings like the ones that you have seen before, and they would like to include all the results in their renovation roadmaps. So we have the 4 buildings that you have seen with Tristan, and then we selected 20 buildings owned by the same owner and then we tried to upscale to the whole building stock of the canton. So these 20 buildings, they have a they are statistically represented. Up you can see how the classes of the heat consumption of the buildings are distributed, and down in the second excuse me, we cannot show. In the second graph, you can see the evolution since 2000 of the heat consumption. You should be in Geneva to have this data and to see the power of this data. They are collecting the heat consumption of all the buildings since 1994. So we have a lot of data to compare and to analyze. And the first question they wanted to answer editing this regulation were measure or simulate. And then you see the Danish measured and simulated by the EPCs distribution, and this is what Michal presented. We have an overestimation of the energy consumption of all buildings and underestimation of the new buildings. And we tried to see on this statistical sample that we had, and then you see what is the expected energy consumption by the EPCs. A lot of class G, they are really very pessimistic, and then you have downstairs the measured heat consumption. And you see that we are not so bad, and this is because it's not only the envelope of the building, but you have also the operation, and there has been a lot of actions to optimize the operation of the buildings, and all these are outside of the EPC. So you lose almost half of the energy if you see only the EPC. So the decision was we keep both, and the measured and the simulated energy consumption. This has a cost, and you have to be very severe on the way you apply this. Not just say we collect the energy consumption. Somebody can cheat, so there are standards, there are methods to do that. So the canton decided to reinforce and to make it more credible. All this declaration is like a tax declaration. You have energy declaration every year. So now they are very strict that you declare it at time. So you have always the updated values, and the owner also, they decided to go with a company offering this service of collecting the energy savings, not the energy savings, the energy consumption according to an ISO norm and according to the EPC operational labeling. Another consequences of looking the real energy performance, there we have seen all the building stock. Then there we focus on the 85 subsidized building for near zero energy building. They should be all of them class A and B, and we see that they have even of class F and E, and this was a shock. This means that performance gap leads to policy gap, and then a policy gap leads to energy failure. You see the group of these 85 buildings, they are consuming more until 2011 than the average of the buildings, and then when they are renovated, they should reach the green line, but they are in 317 megajoules per square meter instead of 210. So here you see the performance gap, and you see the performance gap on the whole set of subsidized buildings. This means that you take the money of the taxpayers and you subsidize things that doesn't really work. But is it performance gap a fatality, or should we accept it, or it can be corrected? And they use the E-DYCE results to try to correct in several buildings, and we have a very good result. They have another program where they subsidize the optimization of renovated buildings, and they are imposing several findings of the EDYCE project, like, for example, the declaration of the monthly energy consumption, not of the yearly energy consumption. So very early we realize if there is a performance gap. And this leads to a rapid correction of this, and we have a very good result is that the first year they are very disappointed to the point to stop subsidizing the optimization. But as soon as you identify a problem, then it was corrected for 100% of the buildings, and we have zero performance gap of all the buildings that were optimized. So this is a good news. Identification of the performance gap. This leads to the correction of it. And here, this graph, it was a qualitative graph in a research project in Switzerland about performance gap. But with this 20 statistically representative buildings, we evaluated this performance gap. And if you compare the theoretical savings of 117 megajoules per square meter with the anticipated savings, we already have a negative performance gap because we overestimate the existing buildings. So we have big ambitions, and we already have lower savings. And then if you compare the performance gap after, if you consider the performance gap, we remain only with 30 megajoules per square meter. Tristan have illustrated that. Here you can see the power of the data. We say that we have in Switzerland this data. If other institutions follow the recommendations of EDYCE and go for both simulation and monitoring, the data continue other information than the data itself. So here you can see that by comparing the energy performance year by year, then you see that first, this is strategically for Geneva, they are not at 600 megajoules per square meter of consumption when the previous regulations were already did, but they were 450. So now the 450 is the target that every building in Geneva, and this is inside the regulation, should not exceed. If you exceed 450, then it is imposed that you apply optimization, because the optimized buildings are better than 450. But here you can see a comparison of the group of buildings that they have a law, and we try to see the efficiency of this law, which is obligatory to change the simple glazing. It is almost applied to all buildings, but not all of them yet. There are some historic buildings, and there you see some non-replaced single glazing. They still consume much more energy performance and heat energy. And you see a group of renovated buildings where this measure was applied. Here we are not subsidizing. Here is not the carrot, is the punishment. You see that it works, and the mean of this group is similar to the optimized building. So we tried to apply this on this program, which is a new program with demand control ventilation. We performed an EPC before, an EPC after. It was me that did all the design of this project, of this program. We have something like 60 megajoules per square meter of energy potential. And then we try to see the energy savings, the yearly, and during 4 years, we don't really see very clear energy savings if we compare the group of the annual energy consumption. So it's a problem. It's a good idea to compare the annual to see if you reach your objectives, but it takes too much time. So we use the EDYCE recommendation for the energy signature, and we see the monthly energy consumption, and this is what Tristan presented. We see that sometimes it's difficult. Here we had two actions that were together, but we know now that there is energy saving, but not the ones that we projected. So, but you can see something other from E-DYCE is that you can apply this idea of E-DYCE of using adapted conditions of use even on the existing EPCs, and just applying on the existing, we pass from 60 to 27 megajoules of ambitions. And if I knew that before 10 years or 5 years ago, when we did this, we designed this program of the state, we would design it differently, because we would have more realistic ambitions. And you see also the power of passing from the yearly mean of the ventilation rate, instead of 0.7 of yearly mean, you take day and night. As during the night you have a lower external temperature, if you stop ventilation, of course, if you stop ventilation during night, you have all this catastrophic CO2 indoor environment quality problems. But by taking into account the DEPC, we are more near to the measured one. So we see that it is a good idea to use the dynamic for dynamic phenomena. But we will not throw away what we have, which is these existing simulations. So the annual monitoring is a minimum obligation. Both the owner, he pays now 600 euros per month, per year, to have a labeled measuring of all the buildings, and they really follow the energy performance yearly by yearly, and they guarantee 3% of deviation of the real consumption. And the canton also, they are paying a lot of money now to make it, to calculate correctly the surfaces, they check the people that are declaring if they are cheating, and so on and so on. At least 2 years of optimization after commissioning is a minimum. In the regulations now it's an obligation after a subsidized, after you get a subsidize from the government, you should declare, not only follow this and optimize, but you should declare, if you declare every month your energy consumption to the university that got the duty to control this. And then for optimization and monitoring, you need at least a monthly time step signature. You can have a lower, more short time step, but at least 1 month is a necessity. So the effectiveness of large energy saving program, it's a must to control it. For example, they have another obligation of installing solar collectors, thermal solar collectors in Geneva, and by checking the effectiveness and looking the real energy consumption, we realize that almost 50% they have a technical problem. They explode because they have overheating. So they are trying to control, to repair these technical problems. This collection is not just an idea and a nice poetic suggestion. You need to organize this collection, and you have to pay the necessary effort. The metering is important, and not only the metering, you should have a clear diagram of metering, and you know what each meter is measuring. And then you have to in the EPCs, we have to have what is the metering measuring and what we should read according to the EPCs, to the objectives. And sometimes you have problems with laws by declaring, for example, publicly the energy consumption. This, what I have shown you, it's public, and it can be public because there is a law obliging all the citizens to declare it publicly. If this law was not there, we wouldn't be able to use this. So the data laws should be taken into account when you are measuring. and if there is a lot of protectionism on data, then you lose all the data because only some, or sometimes they sell them, or sometimes but the community is not taking profit of that. So the last is this adapted conditions of use. It should be integrated in the regulations. For example, in Geneva, you use the standard conditions to define the objective, which is the same for all the citizens. And then when they check if the measures that they are proposing are going to reach this, in a construction permit, for example, they push the people to use the realistic conditions of use, so you see the credibility of the project. Thank you very much, and you will find these results also in the last deliverable of the project that is going to come at the end of the project.
Yes. So with this presentation, we conclude our webinar. I think it was very interesting to go from a single building level and different problems of the buildings, also accounting the indoor comfort, but as well, of course, the energy. These two cannot go separate from each other. What Florenzo said at the last, let's say, when he summarized his presentation, the monthly collection of energy use is a very good idea for seeing if the policies are working. So this is, for example, this is sufficient frequency of data collection appears. But if you would like to understand, for example, the faulty operation of the buildings, this requires even higher frequency of monitoring. Monthly data is not sufficient there. You have to go to hourly data, and from hourly you would have to aggregate probably to the weekly frequency. So it all depends where our ambition is and what we want to monitor and what we want to correct and identify. I hope you have found this presentation valuable. This is recorded, so will stay forever. Deliverables will also be downloadable from our webpage, so you are encouraged to reach for these. Thank you very much thank you all of the presenters, and I think with this actually we conclude in some way a very significant step of this project, so we should give us an applause, and then
Okay, thank you very much. As seen online, we do not have reached the question, okay? So clearly, we will be happy if anything has doubt or question or something to ask. Use, please, the EDYCE portal and things, and we will try to come back to you. Thank you very much to be there, okay? And hope to see you next events and elements, not for the EDYCE project, but in general, and looks, and stay tuned. Thank you very much. Bye-bye.